this video, we'll be looking at the first quantum phenomena topic, photoelectric effect. The photoelectric effect was an observation. An experiment was carried out in the late 19th century, where light was shown on a metal surface. And what was observed was that electrons would leave this surface under certain conditions. Now, as the wave theory of light was the main theory of light, it was believed that any light source used would eventually work. But instead, what they observed was that only light above certain frequencies actually worked. Now, to set this up, these diagrams show the apparatus. You have a container, evacuated preferably, with a metal rod stuck through it. Now that rod is isolated. You can see a rubber bung there. And there's a piece of gold, a very thin piece of gold, so the gold leaf, attached to the rod. And a sheet of metal attached at the top. Now the entire metal section, isolated from anything else, was charged. So it was given an excess of electrons to have a negative charge. And by shining light on it, electrons could be promoted to leave. Now this did not work for red light, and even as you move throughout the spectrum, it still didn't work. However, at a certain frequency, in the ultraviolet range, it was observed that electrons left, and this was seen by the fact that the gold leaf would drop down, and that's because it's no longer being repelled. So this was quite peculiar, but we know from having covered this previously that when we have a higher frequency, we are actually talking about energy. So energy being provided by the light is what matters here. So it's only in the higher frequency of UV and anything above that frequency that this phenomena was observed. And this goes along with E equals HF, because we know the frequency is proportional to the energy of the photon. However, this was obviously before the concept of the photon was conceived. In fact, this was the experiment that led to that model. Now, you're expected to know what was expected with this experiment and what was actually observed, and essentially bring it back to this equation, to E equals HF. So, if we consider the idea, first the expected result being the wave theory, and the observed result relating to the photon model. So if we consider increasing the frequency of the light that's shining on the metal surface, it was expected that regardless of the frequency, you would eventually get these electrons leaving the surface. So it would eventually work for anything. So it just changed how long it took. But in reality, as we've already discussed, there were no emissions below a specific frequency. So this was quite a standout observation. Now, if we consider increasing the intensity, traditionally that's the idea of more waves hitting the surface, or in our more modern concept, more photons impacting. So it was expected that there would be more electrons liberated from the surface, more electrons emitted. And this is what happened, with a limitation. And that was obviously the fact that it had to be above the appropriate frequency. So above a specific frequency for that metal. Now, with time, we've already set if they waited long enough with the wave model, the wave would continuously feed energy to the electrons, allowing them to eventually leave. So it's this continuous provision of energy as the wave continues to feed each electron. And that meant everything should work, every wavelength, eventually. But in reality, it didn't work like that. Instead, it was an instantaneous event. So when a photon enters and interacts with an electron, it gives it the energy, and the electron leaves. But if there's not enough energy, it won't leave. So it's a clear-cut case of interaction in the instant the photon arrives. So tying all this together, the limitation of frequency was the major player, the thing that led to this change. So as we've said, this all comes down to Einstein's suggested equation of E equals hf. So yet again, a worthwhile reminder, E is the energy, so energy of the photon, measured in joules. Don't leave it as electron volts, always convert to joules. We have h as Planck's constant, as usual, and f as our frequency, continually measured in hertz. Now, what we actually get from this investigation are three clear explanations, three clear points that are made by relation to this equation. So we can say that any electron that is interacting with the light is actually absorbing a single photon. So it's a one-to-one relationship, and that is critical. Now, an electron will leave the metal surface if it has enough energy, and we always refer to it as the metal surface, even though it is multitudes of layers deep of atoms. It's still to us a surface. Now, the amount of energy it needs to provide in order for the electron to escape is referred to as the work function, because work needs to be done to escape the surface. And any energy left over just becomes the kinetic energy of the electron as it leaves. So this leads us to the equation that you are given, where hf is equal to this symbol phi, which represents the work function, and ek max. So, as we know, hf is just another way of saying E, the energy of a photon. So each section of this equation is actually just energy, even though only one is labeled as E. We then get phi, which is, as we said, the work function, the amount of energy needed to escape the surface. So as it's energy, it'll be in joules. And finally, Ek max. Now this is the kinetic energy, the leftover energy from the photon using up energy to break the work function and free the electron. Now it's a maximum value simply because if that electron is a few layers of atoms deep in that surface, it may lose energy as it tries to escape. So before it actually leaves the physical surface, it may have encountered other particles, collided with them, and lost some energy. So the maximum kinetic energy is the maximum energy we would be able to observe of any electrons leaving that surface. Now, it's quite important to be able to rearrange this equation and understand it in all its different contexts. Now, obviously, to rearrange for frequency, all we have to do is divide both sides by Planck's constant. There's not a huge benefit to doing this, at this point at least, but it's a useful thing to show. Now, the other two forms to rearrange are much more beneficial because they allow us another way of thinking through what this equation actually represents. So let's consider rearranging work function. So work function being the amount of energy we need for the electron to escape the surface can be determined by measuring the kinetic energy of the electrons as they leave and taking that energy away from the calculated energy of the photon, which we can do using E equals hf. So this is very much a practical application. This equation can very much be used in a lab. So it's a real-world equation. Now the third form, Ek equals hf minus work function, is more of a useful one when we consider graphs, as we'll see shortly. Now let's look back at the frequency equation for just a moment. We have a situation where an electron can be liberated from the surface but have no remaining kinetic energy. That would tell us the exact frequency needed for that work function to be met, to be made up for. So we refer to this as the threshold frequency, f with a subscript 0. Now, in order to find this, we can use this rearranged equation for f, where f is work function plus Ek divided by h. But we know that if it's the threshold frequency, Ek max is going to be 0, which leaves us with a very simple formula, f equals work function over h. Now this equation is not given. It is a simple relationship that you're expected to be able to figure out from the equation that you do get. And realistically, it is fairly straightforward. You just have to remember that when the electron is first liberated with exactly the right amount of energy to accommodate a function, it will have 0 kinetic energy. Now, what we need to do, and you need to be able to recognize and use in the exam, is this graph. Now, the graph will have energy and frequency as its axes. So the y-axis will be Ek max, and though it could be listed as electron volts, for example, it's very often done in joules, where they've taken out the times 10 factor and put it in the units. So, for example, times 10 to the minus 19 joules. This is often done to mislead you so that you miss it when you're carrying out calculations. So don't miss it. Similarly, with the x-axis being frequency, you very often find this to be listed as times 10 to the 14 or 10 to the 15 hertz. So again, don't miss that factor, or it will drastically change your results. So the graph itself is a simple straight line graph like this. And the straight line starts from a point that is not 0, and in fact that point has meaning. It's the first time that the electrons have enough energy to escape, so that must be the threshold frequency, f0. Now going there, we can use this graph for a lot more. And whenever we have a straight line graph, we should use y equals mx plus c. Now if we plug in what we have for y and x, we should be able to recognize the fact that this matches up with one of our equation forms that we just looked at. So we know that Ek equals hf plus c. Now in this case, that c value, the y-intercept, can easily be seen to be negative. It'll definitely be in the negative region of the graph. So we'll come back to that. We know m represents gradient, which means our gradient here must be h, Planck's constant. So in the exam, you may be expected to graphically determine this. So using the classic triangle method, change in y over change in x will give you your value for h. Unsurprisingly, this will not exactly match h from your datasheet, because that would be too easy. It needs to be slightly different, and it always will be. So show your workings clearly on the graph. Now c in this equation was going to be the work function, and this is not always possible to find graphically. But if they give you enough space in that y-axis that is negative, you can find that y-intercept, and the magnitude of it will be your work function. Otherwise, you'll be expected to use the equation to calculate it. Thank you for your time.